food texture analysis. This is basically on the subject of understanding and its application. Chairman sir, registered participants is 385, and so far 74 are in Zoom link, and other people are there in the YouTube link also. We're live streaming this program, and we are expecting more on this Zoom platform also. So with this, I welcome our chairman and the project coordinator from Central Institute of Agricultural Engineering, Bhopal, Dr. Din, and I request him for a few words on the today's webinar, food texture analysis.
Sir, this is the good time कि our SMD is discussing what will the future of our agriculture engineering and mechanization in 2047. So in that area, what we are doing, this topic is very relevant. As we know, this in this direction, R&D has done very less in point. So therefore, there is need to take more project R&D discussion on this part and using this tool in analysis, and then therefore in this area we can make the progress. And there is need to also do something to incorporate this thing into the at the academia level also, because when our students are learning, they have not understood this topic. So therefore there is need to also introduce this topic for academia, and there is need to also collaborate with industry. As you know, our Coimbatore center is working very nicely, so there is need to make collaboration, and there is good collaboration with industry in this institute. So there is need to strengthen the collaboration, and what work we have done, we have to validate by the others analysis type also. So in few words, I congratulate to organizer for conducting this program.
In about 50 minutes or so, we will be discussing on the topic food textural analysis. Of course, many may be knowing this, and my concern of this lecture is to have an understanding on this and how best we can apply in our research, and then how statistics or some advanced statistics that we can use in this area, and then what the material scientist people, they use the rheology as a term inclusive of the texture more than the sensory, more than the texture. I mean the food technologist, how best we can use this. I know that this instrument may be available in almost all the greater institutions, and application side, I like to have some of the understandings what I learned through across the years when I was working with CIPAT Ludhiana, and then CAE Bhopal, and working now currently at this regional center Coimbatore. So we like to have some of the coverages like concepts and understanding, some food properties measuring instruments. Of course, this is not the only one instrument that will cover up all the things, but we have the list, but then no, we are concentrating on the food texture analyzer. Then when you say this one, it goes with the graphs. So typical textural analyzer plots or the graphs. So I'll be showing so that we can have an understanding how the range of the plots we can get, and then TPA, texture profile analysis, and then test procedures. See, generally the people goes with the procedures, whatever else in the literature, they adopt for their sample, whatever it is, and then they go for it. How to have understanding on the test procedure. That's what my concern here. And the case studies, some of the works of mine, and then the date of mining, some of the tips. So what statistical tools that we can use for, and then experimental illustrations. When I say the compression or the tension or the kind of the penetration or whatever, and what some experimental illustration, so that small animations will be there in my presentation, so that you can have an understanding more. And then some experimentation tips where we in the sample holding or getting a data where we do mistakes. So I am putting some of the things, and then the Rheo and finite element models that we can derive from these force, distance, time, the basic units, that is fundamental units out of the graphs, what we are getting. And some of the audiovisual aid that to show the how the experimentation takes place, how the procedure we can follow. See, we know the texture. Somewhere now people say the rheology. In broader term, rheology, and then the texture, when it comes for the food technologies, we say mostly on the texture. When we say the texture, and there is always a controversy or a dilemma, what is texture and the structure? So I like to say here, it is an attribute of a substance resulting from a combination of physical properties. Simple quotation I am giving. Otherwise, n number of definitions are there. But then no, I am to start. I am going with this. This is a kind of a response. That is the attribute of the substance. The food is there. How it respond for some physical combination, the structure it has. Then what is it? What is the structure it is? It is the nature and the relationship between the components. That is the arrangement of the material of the food. So this is like a arrangement, and that is like a response. So you can understand what is texture and structure. Now, why the texture for today's topic is? It is mainly when the people say for any product, they will be saying that, yes, texture is not good. Texture could be anything, maybe gumminess, stringiness, springiness, or resilience, or the stickiness, or consistency. The people say the texture is a main focus that criticizes, oh, that is not that crispy. That is not that is very soggy. So the people comment rather than the taste, rather than the nutrition profile that needs second level, third level analysis. But the first sight itself, they say the texture. So thus we say here also we say the firmness, strength, and then toughness, all things. And engineers, I could see some of 20-25% of these participants are engineering side. Of course, they are food engineers, then agriculture engineers. But I could see some of the people from electronics and then from mechanical engineering, the material science people. For them, the strength is in a different perspective. Strength means how strong it is always. If they are constructing a bridge or a beam or a pillar or anything, they want to have a strong. But then no, what we are talking today is at what point the fracture occurs, at what point bioyield point occurs where a food become palatable, or we can in our jaw, in our mouth, how best it can size reduced, and then we can consume. So that way they look in the upper side and we look always in the lower side of it. So where we are opposite. What is food texture? Is it a science, engineering, technology? And many of the time we try to link with the sensory organs of human beings. So sensory organs means we know by touching and then feeling, by seeing, hearing, so on and so forth are there, but then know how best we can take this subjectivity. See, that's what the researchers, we try to eliminate the subjectivity in our programs. Subjectivity differs with the people, those who are in the panel. And then how to remove those things, and can we put the objective measures, and that will be good for a statistical analysis. If it is so, you can interpret and that can be published. So that way it is a science, and then more than engineering, and then it's a technology. Here whatever we do here, we are not talking about the chemical aspect of those things, how the chemistry involved in this, in sensing those things. We are not doing so. This is a physical measure where we can corroborate all this. This is a group of properties I'm putting in a advanced terms, like it's a physical, mechanical, and rheological, from food to structure. So what I mean to say is here the mechanical and rheology means the rheology, the food comprises from the solid to semi-solid to liquid, like that. And if it is so, and the coverage total, the rheology comes in. That way, I'm so many differences are there. For my presentation now, I'm going with the composite. This is a composite. That is a we can say it's a combination attributes. that arises from the structural elements of foods, the manner in which it registers with biological senses. So how our body senses with the food product of our brain stimulus, how it is manipulated, how it is reflected. It is a combination of all these things, the physical, mechanical, rheological, how best the attributes develops. So this is in the area of sensation or kind of the sensory attributes, how we can put it in the terms of the objective terms. So as a layman, I'm looking the food, yeah, texture, the word, and then it always towards the solid. To some extent, it will be coming towards the semi-solid. But of course, many of the time it will be with the solids. And another one is viscosity. When you say the viscosity, and then many of the time it goes with the semi-solid, but it has a leverage moving towards the liquid. I mean to say that very thin, like a soup materials. The objective measures, what we are doing is, it's a function of the force, distance, and time. The force, distance, time, you agree, all these are very basic units. You know, all these basic units, from this force, the distance, time, you can go to any level of the joule or pressure terms or kind of, the work energy or whatever the engineering rheological terms it goes, you can measure. So I'll put this term like this: perception, and we are sensing the human nerve. And then for our understanding, when you take the food, it stimulates, and it stimuli goes sensation and the perception, and then it says communicate, yeah, this food is something maybe hard, maybe soft, maybe consistent, maybe viscous, whatever it is. So this thing, this closure cycle, we want to put it in this basic terms. There was a survey how important the texture in food. So you can see the first the row, the texture, it says 51%. So 51%, it implies that the texture for any food is very important. Okay, we talk about the food texture, and it links with some of 3-4 items like perception. Okay, how we perceive the things. And another one is social, cultural, physiological factors, how it goes with our own the human race or region, or how they are into the habit of having the food. Another one is the parameters, how to measure. So mechanically or geometrically and other terms. And how we can evaluate with some of the instruments. So always we say as a food, but I consider in the textural point of view, it is mix and match. Many of the time the mix goes with the well, and then again we have to match for some of the things. And the pro and con effects will be there. So some people will be saying smooth, or some people will say the food is moist, sticky, crunchy, crispy, dry, creamy, chewy, chunky, tender, and so on and so forth. But for a product, may have a difference in the range of, suppose if it is a smoothie food, no, smoothness for a butter, it should be so. The degree of smoothness, at what level it has to be. Then the texture, the instrument, it is very important. That is very important. Suppose it's a cohesiveness with the temperature, or adhesiveness, or the consistency. So it gives repetitive value. When the repetition comes, online measurement, when you are going for online measurement gadgets development, these basic values will give a lot of understanding for your research. Of course, no, the food we say as a processing, many will be there. Suppose if you are storing a fruit, it's a dried fruit. You are drying, and then you got a dried fruit. The hardness will be increasing. How the hardness, the cause, loss of moisture, and then the protein denatures, and then especially that whatever the structure in that, or the proteins are there. And another one, when you put the fish for storage and then you put it in the frozen condition, if it is so, if that is toughen, it is not strength. The strength is different, toughness is different. The toughness goes with the graph, the area, and the strength means that it goes with the hardness and the firmness values. It's a single. Suppose a Newton means it's a Newton. Now, suppose toughness is Newton second, that the area of a graph. We will see when we go with further slides. So like this, when you see the textural changes with the, this slide is for the storage, how it behaves. Suppose ice cream. Suppose it's a coarse ice cream is there. Coarse. What happens means ice crystals enlarged. Then another one is butteriness, clumping of fat globules. The fat is more, and then from there the butteriness comes, and then it is going sandiness, crystallization. So the first one is crystals form, but now in the stage of crystallization, and then crumbliness, the poor protein hydration. So like this, you can link with any of the functional properties of the carbohydrates, protein, and then you can study for yours. Restricting those things, I'm coming the concept of the rheology. Broader terms, deformation and flow. Deformation means always we say as a elastic and inelastic. That we say plastic. So many of the time we go for the solid food or semi-solid foods in this range, Hogan and this and that. For the understanding, elasticity means it's like a spring. Okay, when you compress, it will come back to the original within no time. Suppose pastry items. Okay, suppose you are pressing that one and then you are releasing, and it will press, it will come back to the original, but may take time. It's one thing. Sometime it will come to the original point, but having a loss. Suppose for an understanding, suppose you start with the number 10 and you are pressing to 6 and you are releasing, and that is going to 10 means it is elastic. But it is going towards 10, but then it stops somewhere in 9, 9.2, 9.5, and then whatever that one 0.8, 0.5, that unit will be interesting to study. There we can go for creep or kind of other studies. I will be showing how best the engineers can take this value, and then with the models of Maxwell, Kelvin, and then generalized models, and then they can go for publication. These are some of the terminologies. Since the material scientists are also here in the platform, I am putting this. Other terms, if you look, people say not only the force, distance, time, I can, when I put the area, then I can go for the stress, normal, then so many so forth are there, and torsion. So of course the torsional, now we are not dealing much on this, but I will say where we can go, and then shear, true, fracture, all the time we do, and then the strain, it is associated one. Here we will be using the pressure, deformation, bio-yield point, rupture point, bio-yield strength, elasticity, plasticity, toughness, and then mechanical stresses. So when we go for this dynamic study of this, and it will be so interesting to have a lot of data. I am giving some picture for you. So this is a material, you are giving a force, applying or pulling maybe, and something occurs, it's a deformation occurs or enlargement. Deformation may be either compressive or in the expansion, maybe in the linear terms or in the volumetric terms, whatever it is. And then the material, it goes with the linked with the material property. So where the stress strain will be coming, and a lot of models we can go for. So I'll go with some of the food properties measuring instruments. Okay. So why we need sensory aspect, we know many of the things, but then why to go for this sensory panel? This is so expensive. Before your information technology, when the information technology came, and those people are paid highly, or otherwise, these tea tasters, I think coffee tasters, they are the one paid maybe the highest salary in the world. So getting those people for the food to test, and that will be very typical. The coffee and tea, I can understand for 200 years, 300 years, it is going. But then no, if you see the products now, 30, 40 years, so many products are coming in. How you will get the panelists? Of course, for our research or kind of the publication for our project, we make a questionnaire, we give to our own colleague or the students, and then no, we collect some of the information, having some hedonic scale 1 to 5, 1 to 9, and even 14, and then we rank something. Okay, for doing so we do, but then are the panelists, are they are eligible to do this? So these questions are coming in. Okay, today they did it. Tomorrow, when you give the same product to them, the next time, will they able to do or assess the same thing what they were doing on that day? It's again a problem. So far, we were talking about these fundamental and how it is imitated, and then no empirical formula with the force distance time, and then we can make a model of the ideal one. That is what we are going to see as a textural analysis. Of course, you would have heard of many things like farinogram, mixogram, extensiogram, alveogram, peristrogram, textural. So many are there, but all the I mean, the food scientists, food technologists, those who worked with this instrument, they can say all these have different units. But that unit, it is not like a fundamental units. That unit you can't convert anywhere. You can carry the value, you can carry the unit, that's it. You can report. Can you put it in one platform for analysis, for statistical understandings? No, that won't allow. That's what the farinograph and this and that. Those things are fixed with some of the concepts that is very close to with the, suppose if you are working with the dough for bread making, that is it. One instrument for that purpose only. I think people can understand now. And then no, the mechanical engineers, they can understand this. The Instron, that is the company, then universal testing machine. Generally, they say UTM. And that UTM, now we are going to see the share model, that is what texture analysis. The texture analyzer is like we have single column and then double column. The load cells could be 5 kilo or 50 kilo, and then it ranges to 1000 kilo even nowadays. That much accuracy. So it is a list of the text analyzer alone. So many, more than dozen companies are there, and just to have a glance of it, I have given. Otherwise, I'm going with typical one food texture analysis. We have seen this is the one UTM, and the same thing here. It is the texture analyzer. The texture analyzer, here we have an arm, and that will move up and down. Okay, when it comes down, this is called compression or penetration or whatever you can do it. And then no, when it moves up, then always you work for something the tension side. Okay, so the upper right side, no, this is the illustration. See, it is compressing and it is going. Once it started, and the graph also starting, it goes back. See, the probe touches, and the graph starts, and then completed, yes, then it goes back. So like this, we can see some of the interesting animations, and then how best we can understand. So now it is linear movement, either up and down, and then it can be like a compression or the stretch. This is a traveling arm with load cell and recorder. The recorder, always it will be the display like a graph. And when you double click the graph, and then you can go for X, Y, Z. I can say force, distance, and time table will be there inside. I mean, when you double click that graph, and you can see the individual data. So every point you will have 3 data. You may be asking me, research, getting a data takes a lot of time. But when you do a study on this text analyzer, within second, in a second, you can fix your recording values. Could be 200 records per second, or 500 points in a second. Means what? In a second, you will get 500 X, Y, Z. That is force, distance, time values. Suppose you do for 5 seconds, so you will get 2500 data. So data means 3 data, 3-dimensional. You can go. These are fundamental. You can put it like a stress, strain, then Young's modulus, or kind of Joule, or kind of kilopascals, whatever the value you want to carry forward, and then you can convert and then you can move. Suppose if it's the consistency, and then you can have apparent viscosity, and then you can link with the how much the value is. Okay, that way this instrument is so good for your research. Okay, just to have an illustration, I'm putting compression, tension, and bending. So it is like, no, this is the platform. This is a sample. When I compress, I'm expecting that, yes, deformation, suppose maybe 10 mm sample, I am pressing, yes, it will go to 9.9, 9.8, I would like that, it will go to 9. During the time, what happens for some of the products, there will be a bulging, there's a busting. Suppose you have a tofu or otherwise cheese, this will have the effect like this. In many of the time, we ignore. What we do is we compress and we get the data, and in the maybe interested to have the one data, what is the firmness, what is the failuring point in the graph, only one value, and we will note and then we will forget. Neither we use the XYZ values, or the understanding, the minute understanding of the busting also takes place. Why can't you take the busting value in your research? So that's what small tips I'm giving, so that it will give an understanding to you when you do with the samples. I'm not saying always for all the products. Suppose example, some cake is there. Then the cake, in some of the cakes, what happen? It won't bulge, but it will go inside and it will come back like elasticity. You can't see a volumetric expansion sideways. So I'm putting the illustration, see how the probe goes and how the graph goes and then comes in. Okay. Now another one, penetration. Here, when I touch this right hand side, here top, I am putting probes comes into the contact of this product. Once it touches, at that time it is compression. That time it is a compression. When it start to penetrate, that will be a very different one. I'll put another graph, other slides. I will try to explain what it is. I am saying. See, this one here, it directly have a meaning with the area here. But once it penetrated, the increasing penetration, and that will create, there is an incremental in the area plus circumferences. The perimeter also comes in. Many of the time we doesn't understand, and we never include in our any of the research. If you do, and this will have a lot of understanding for you, we can do that. So another one, the tension. Okay, the samples standard sample size are there, and you can go with that. Or otherwise, if you have some standards you want to create, that also possible with the whatever the product you are working in. So far we were seeing this graph, the first quadrant, but here we are seeing in the fourth quadrant. What happens? The tension means the compression, they put it in the first quadrant. This x-axis and y-axis always plus. Here that is minus and then plus. So that's what the tension they have put. They have educated that textual analyzer in that way. Compression means positive, and then tension means the negative. Another one, 3-point bending. When you go for purchasing any bendy or lady's finger or any slender the fruits or vegetables, you try to do with the 3 fingers, try to see that how it is. Okay, if you have a pasta, then before packing you try to see how it is breaking. So this is one of the things, you have a sample, and then these are the simply supported like a beam, what we study in strength of materials, and then these are the 2 points, and this one is the opposite point. Suppose when you press like this, Suppose my hands, when I put like this, what happens? We say somewhere the compression takes place. No, the compression takes place at the first instant, and then closely when you look in the outer layer of it. Okay, this suppose this one I am putting like this, and whatever I'm giving is this is the compression, and this 50% less than this in the pencil. What happens? No, these will be like shearing, and then tension will be there. Then it will be a failure will be occurring. I think you can understand best. So when you are making for the models, beyond the compression, you have the lot of scopes to study the shear and the tension into the model. And if it is so, and then your study will be more stronger. And typical TA plots I'm showing. And many are there. I will go one by one. But for this slide, I'm saying this. Okay, I put like a stress and strain. Leave this one. You take a say this is time and this is force. The first straight line up to this point, it is like a elasticity. When it comes to the point 2, this is what we say as a firmness. In some of the time, it will be like a fracture. So I will show the fracture and the firmness or bioyield points in the further slides. The bioyield I'm saying here, it is related to the failure. See here, the point 2 is a crack occurs, and then point 3 you are getting a complete crush. Then after that, something is going, and then product may come down and go, or otherwise it may go somewhere else. And then here in this typical graph, we have the 4th point is the rupture, complete rupture. So up to this point, there might not be a very visible deformation, but then the crack will occur at the point 2. But sure, the deformation will occur in 3 and 4. So these are the 3 interesting points, and in this graph. When you say elastic model, you want to have it, and this region will have a good base for you to study. I'm putting 5 typical graph that you will get it in this. And more than that, whatever you are getting, it is derived from this. So if you have the understanding on this, what 5 graph I am showing now, then you can extend to any of the graph models you are getting in. And then, so another one is the beauty of the textual analyzer is anything you make error also, that will give a graph. That's the beauty. Suppose you are not put the sample correctly, or otherwise the probe has not sensed the trigger point and it went away, and then also some graph will come. So all the time you will be getting the graph, but as a researcher, you should know the nature of the food, what the sample you are bringing in, the sample you are putting in for the measurement, then you have to go for it. So first one, the A graph. Now what happens? The first point comes here. After that, it is reaching. I will say an example in the 3rd slide now, and see it is going like this. What happens is the skin is softer than, suppose you have any product is there, the skin is softer than the inner. Here the less value, when it goes inside, and that's the distance. I am putting, say I'm going to the sample, and the first one is soft value. Then again I'm going, it is giving a higher value. Means what? The stuff of the material is stronger than the skin portion. Now, second, the skin and the inside one are more or less same. Another one is, yes, inside material is so soft, and then outer material is harder, maybe egg. So the shell will be so harder, and then if I touch that breaks, then inside nothing will be there. I can go inside. Another one will be there. Here the graph, the first one, we were having the clear cuts are there. You can measure it. You can move in the graph. I can move the cursor and I can click. I can take the point. But here it is not so. It is somewhere it goes like this. So I can put a drawing, but even I can put the cursor and I can get the value. But if I go with the tangential modulus, secant modulus. I think engineer can understand on this. If you draw something and you can go with a model, and then you can have a, see, there is a journal of textual studies exclusive for this. All the models they will take, and then for engineers that the journal will be so good for you. And then only the 10th mathematics, 11th mathematics, you will be playing with that. And then in this textual analyzer will give a lot of data. That's what now I said, within 5 seconds you will get 2500 data XYZ. And then the graph E, generally the EB doesn't appreciate, but of course it may come for some of the delegated the samples. But then delegate samples, these samples, when we are working, really textual analyzer is not advisable. So the first 4 graphs, it is good, and to have an understanding that will be repeating. And I will show now see how a potato will be there. The potato, the skin is tough. Then after that, inside is, that is a very starchy, the starch material. So starch globals, starch materials, when I pierce it and it gives up space, and then it penetrates. Cucumber, see how tough it is. Then sudden drop is there. There will be skin. After that, there will be voids, and then seeds will be there. That arrangements will be very loosely packed. That's why you are getting a stick. Another is squash, carrot. Yeah, you can see the carrot is somewhat resistance is there here. And then beetroot, yes, the value is more, and then it is like this. I'm putting a array of matrix. You can see in any of this Borne book 1965, and it is again they went republished in 1986, and now also they are republished in the internet. Also, it's available. You can see this how it is. Now, so far we went with the only the compression or the tension. That is the downward movement of the probe or the upward movement. Only one time. Now I'm going to texture profile analysis. What it means, it will the same thing. A compression means one time, it is coming, again it will go, again it will come back, it will go. So 2 times bite. I think this will show to you. See, first one it is going. Yeah, we were getting in the earlier graph, and then we got it, and then drop again after some time. Again it's going for the same sample. So now 2 cycles, I can say 1 bite and 2 bites. So it is a first cycle, second cycle, how you are getting the graph. In the first cycle, as any graph, you got this. Okay, this is a fraction, small things, there's a fraction. And here it is the hardness or the firmness, and then it drops, again it comes here at the 0 point, again because of the samples. Now TPA is not meant for always for the very firm products. So when this graph drops here, it shows that somewhere stickiness is there, the further product. And then we are waiting, it goes to the original point, and then it waits, again it come back, again the graph starts. Now I think here some of the values are there, then I can see, you can see this area, this A for understanding, just for understanding. The first graph A1, second graph A2, and then the A1 graph is divided into A4 and then A5. Okay, why? Because we can derive many terminology out of that. And then what I was mentioning for the single bite or single cycle, I was saying for a second you can go for 500 data. Means here more than this we are working now. So you need the graph where to split and in what way, whether it is a Newton or Newton second, whether it is a single value, the force, or otherwise the area. So like that you should know. And then we should measure this L1 and L2. Many of the time people may have a doubts on how to measure those things. Yeah, like any graph, you can measure this thing on the site of it, on in the software itself, or otherwise you can get from the values what you got as a data. From there also you can do, or otherwise what you can do is you can write a macro. What we do is a macro in any of the MS software, the MS Office or Excel, anything, you write a macro. So macro is what that you can write what repeating occurrence of anything from the plot. You can type it and you can make it a small program, and then when you link with this graph you obtained, and you will be getting all this value in another Excel sheet. So it is up to you how to do that. Now we will see what it is the fracture, what is the firmness or hardness, and then springiness, resilience, gumminess, chewiness, so on and so forth is there. No, fracturability, I think I told also you can understand best. The hardness, yeah, many of the time, it is looked as firmness. Some people say as a soft, and then some people say hard. No, material scientist or otherwise, some people say, no, the biscuit, no, it has to be like this, or the potato chips has to be like that. No, so many hardness differs with the products. Even the people say apple is crispy. See, you can understand very well that potato chips is crispy, but apple is crispy. If you go with the quality parameters of the what I can say is apple, the crispiness of the apple comes first. So what it means for a potato chips, what it means. So you should know when with the experiences, you can understand what the meanings are, how best you can derive those values from this textual analyzer. Cohesiveness. Of course, know the cohesiveness of any product is bondage between the product, between any elements in the product. Suppose the adhesiveness is the surface to the material, or suppose I'm making a glue. Making a glue, if I am putting a surface, I am making sorry, this is a surface, I am pasting a glue, and then I am putting another surface. Now I am pulling the first one. Suppose the first one comes from the surface of the second one. That's what adhesiveness. The more you study for the adhesiveness, means what? The surface of the first and second, it is attached with the glue. Now the cohesiveness says, suppose the first layer, second layer, okay, it is there, I am tearing it off, but then no, it is not tearing in the range of the glue, but it is tearing in the first sample itself. Means what? The glue is so stronger, so cohesive, and that's not allowing to separate the layer 1 and 2. So like this, you can have the understanding of this. The springiness. The springiness is what, say, you can many of the time people will be having doubts or the misinterpretation on springiness, stinginess, and resilience. The springiness always it is a distance. That also stinginess also distance. Suppose the spring means how revert back. Suppose it is the elastic range. If it is come back to the original or towards the original, and the springiness value will be significant value. Suppose stinginess is there. Suppose you have the fibrous the arrangement in the product. There is a stringy like material, means what I get like strings are there, and then that will resist your force, and then it is here also the distance only, but that sponginess or this stringiness is well will be very different, the understanding wise. Resilience. It is like a rubbery materials. When we say rubber chappal, like in the first go, the chappal will have a lot of cushion. And then after 2-3 months, the resilience of the rubber will go down, and then it will be like a wood, it will be harder for you too. That comfort won't be there. So this is what the resilience of the food, and then we can go for gumminess and chewiness. That is, these are some of the derived values out of those values. Here, I would like to say is, suppose your adhesive value is more than the cohesive. The sensory people know, they will be looking for this, whether it is sticky or not. As I was explaining with the example, this adhesive force, this is more than the cohesive force, then it is the product is very sticky. And if it is reverse, this is not sticky. Okay, many of the time we go with the test procedures of elsewhere, the literatures. Now, typical one I'm taking here, I'm putting for a TPA. There will be 3-4 default something will be there. Dummy also will be there, but I am putting the active the icons. Pre-test, test speed, post-test, and then no distance and the time. Suppose you have a sample, you want to penetrate into the sample 5 mm. That's the 5 mm here. The 2 seconds you are going in. This also you can dictate. In some of the, since it's a TPA, this time is coming. This also active. Why? Because if you see the graph of a TPA, there will be a first graph, first cycle, second cycle. There will be a small gap. That time is here. Or otherwise, when you go for any compression test or single compression or kind of single tension, either distance will be there active, or otherwise time will be there active. So it means that your sample, suppose 10 mm is there, you want to study the behavior, penetrating some of the things into that 5 mm, and then you are going to read some of the things. Okay, you are starting the probe from somewhere else, and then you are going to touch. But you are touching, so I'll, okay, I have a different graph, then I'll show how it pre-test speed, here it is 5 mm per second. Means what? Fast. Test speed is 1 mm. Yes, very cautious. I want to study the 5 mm in the sample. That's why I am going with closely with 1 mm. After once my experiment is over, and then I have to come back. The load cell has to come back. So then the probe has to come back, means, and then also I am increasing the post speed. Now I am giving a sample. My probe is not touching. Here it is there. It is going to start now. I am always 3 mm per second default. Sorry. Now I am touching. It is coming now. Second one I touch. Once touch, it will the probe. This will be active. See this graph active. Test speed when I am penetrating. Yes, it is showing. So it is simultaneous. And now the probe is going back. Yes, the fall down. Now your graph is closed now. Some of the case study, data mining, experimental illustrations. Okay, the left side one, you have, yes, I showed to you, there is a fracture, there is a firmness value like that. But here, all the time, yes, it is like, small ups and downs. Small ups and downs. See, this is like a product of kurkure, like a corn extrudates, rice extrudates in the extrusion process. So it will be so crispy, all the time the voids will be there. It will so crispy. When you're biting, it is giving small smut. So that much crispy. When the crispiness of the extrudates kurkure is the graph, so many things are coming, then the product is so fresh. So fresh. That's what you can understand. And that can be put it in a different graphs, so that in the sensory analysis you can go. Okay, another one, the same thing. So I showed some of the pre-test and the running test and other thing. Here in one of my studies, what I did is I want to see the floor, composite floor compaction behavior. What I did is, okay, when I was working for making a small machine for pasta or vermicelli extrusion process, cold extrusion process, I thought of making a small gadget and then no with a load cell, and then I was trying with this textualizer. It is very possible. Many of the time, no, we stuck up with the probe the what the company has given to you. But then no, you have the option of calibration and then the load cell changing. And if you are well versed with that, and any gadgets or anything can be calibrated, and you can put it in a position that no, you can make your own no understanding. Here, I doesn't work with the, see my graph, this is stress and time. I'm not gone with the force and other thing. What I did is the known area, the known volume, as I told, no, when I am pressing this one, there will be arrangement of the material, the compaction, then afterwards, the products will be coming out. So what I put is what the material, the composite floor with the moisture behaves. One is with 100 Newton, 200 Newton, 300 Newton, and then 400 Newton. What is the behavior? That's what I put it. No, you can go with compaction density. And so it's an article, and it is available. I have one slide for you. And then if you see with that, my presentation will also come in the YouTube, and you see there where this paper has come in, and what are the small bulk density to compact density, the loose density and other thing that can be derived, and the more cycle. See, the many of the time, we study for the compaction behaviors in the material science. So that also you can do. So you can see some of the idea from that paper also. So the text analyzer can be of your use with your understanding, taking to the level of the research. What do you want to have? So another one, data mining, and I'm saying like Pearson correlation. We do correlation and regressions. Pearson correlation will have an understanding of the objective measure and the subjective measure, what you are doing with the sensor. And that can be like a Pearson coefficients, and then that will be help you in writing your data for publication. And so right side, it is the idli, simple idli. Suppose if I give this idli for text analysis, what you will do? You will prefer, sir, okay, or compression or otherwise a penetration, sir. And then afterwards, then okay, why can't you go for a TPA? Like that, you will be saying. What I did is in the sample preparation, see the surface of it is like in the oval shape where I will touch. So I have some other slides where we come with some of the errors. So what I did is for the text, this idli, 1, 2, 3, like no, in the center portion, I took like a small cylinders. Once I know a cylinder, the dimensions, and then I can go with any stress, strain, or whatever the data I can have. So this is there in the Journal of Food Preservation Studies. American journals. So nothing we did it. The sample preparation, I took some caution, and that gave a lot of meaning in the engineering side. And then we went with the paper of Rheology. Another one, as I said, we get a lot of data. As you know, the response surface methodology, one of my webinars I gave last year, and then people would have thought of it. This textual, the response surface methodology is for reducing the data. Yes, fine. To reduce what? When you are going for a research or conducting a experiment, before to that, you can reduce the run. That's what your response surface methodology will do. What this PCA is, principal component analysis. What it does is, once you went into any of the research or completion of your experiments, you have a lot of data. Now you want to reduce, that's what we say cluster analysis, and then PCA, that is principal component analysis. So I put 5-6 values. This is out of the textural. So what is that? TPA, texture profile analysis value. So you can see the firmness, gumminess, chewiness, resilience, springiness. No, so that value, if you put it in this data mining techniques, and then your paper will have a lot of reach. Okay, so I put it on the word. Yeah, you can put it in the regression correlations, and then whatever. And this is one of the interesting one. When we select bending, that is ladies finger, what we do is we go for a 3-point bending. So all the time we go with the snipping of the top of the poem, that one, lady's finger, the top one. When we were doing with the gadget, the cutting equipment, what the instruments supplied by the textile analyzer people, but it was not cutting really. What the bendy will have a fiber inside, no, the long. When we are going for, see, we were studying the MAP, modified atmospheric packaging. When the storage extends, the lot of fiber formation will be there in the bendy. Suppose if I go with the cutting tool, what this textile analyzer people gave, I could not able to get any data. If I am starting to cut, that is a blend one. When I am cutting, no, it is bending that. Instead of cutting, what I did is I put we use the razor blade, no, for shaving purpose or anything. That blade has the angle. That blade has a definite geometry. They cut the strength, all these things. We put it in a frame, and then we calibrated the equipment, and then we got a wonderful data. And then, no, this is there in the Horticulture Act top. So it's the NOS rating is 10 plus. So you then also what we did is 1, 2, 3, the portioning of those things. Then we put up plungers like this, and then we got, and it was giving a wonderful relationship with the formation of fiber, with the storage time of the modified atmospheric packaging O2 and CO2, and it was corroborating in the value in such a way. It was so good to explain in research. Another one, the backward extrusion. So this is the backward. I think I'm not sure that. Okay. Where we can have this consistency and adhesiveness. So I'll go somewhat faster. The time is now it is 1 hour is over. Okay, so like this you can go for spider graphs, and here you can understand the data, how we can put in PCA that we get from this textile analyzer. The adhesive test, see this. The same thing, graph moves, just a little faster I'm moving now. The same thing, but the graph nature, if you see, this will be very different. Here, the forward extrusion, see the forward extrusion, it is coming. After that, it is coming out. Till some point, see, it is coming now. It is touching, again, nothing is happening. Now it is coming. See what happens to the graph? See this graph. See, A, B, C, it is going. After that, C to D, it is always your product is coming out, it is extruding. That's why, it is constant. The graph I am putting like this, you can read these things, how the A, B occurs, from there, the value you can have it. Now I am going with a backward extrusion. What happened, no? See, the sample, rises. Plunger goes inside. Here there is no outlet. It is going back. It is like a tumbler or a glass, like a gel in the glass, and then you are putting the plunger inside, and the volume rises. So that's what the graph says. This upper portion, this area is consistency or apparent viscosity. Then this is what adhesiveness. Stickiness, yeah, same thing. And then some tips. Okay, so as I was mentioning, if you double click this plot area, what we are getting the force and time, you will get the force, distance, times. Yes, how many values you are getting in. Okay, now many of the time, we say, sir, I got a graph. Your advisor will say, okay, you got a graph. You go for this first value, fracture, and the top value as a firmness. You get that data. You come. So 10 samples, okay, 10 graph, and to have this only 2 values, you come. Suppose you are going with this. So this is one graph. The same sample, when you're doing it, somewhere it is coming like this. The first graph and second graph has a different meaning. See, here the product is fracturing, and here no. So if you are not noted that one, suppose your advisor says only the firmness value, you take it, and what you will do, you are missing this value. And another one, That's what I have shown here. Another one, as I was mentioning, 500 data in a second you can go for. See how the rough and the fine data you can get it. Suppose you set that software that in a second, you are making 50 points per second. See the roughness of it. Okay, you are conducting the study, you are getting a data, but these points are discrete and these are very closer, the same graph for a same sample. And what happens, you are getting a lot of things here. This has a lot of data. Once the data are more, I think you appreciate and understand, if the data are more, you will get a lot of good results. Okay, and see the same thing. Suppose the advisor says you take the one value firmness. No, the something, it is behaving like this. If it behaves, this will be a brittle, or crispy, or friable. All these things will be there. Suppose for the same point, if the graph goes like this, less crispy and then deformable, and this understanding is so important when you corroborate this value with your sensory values. Okay, the samples you are taking, suppose this is a sample size, you are going for a penetration. This is right, you have a lot of space, and then you are going, the sample is small, and then you are doing it more, it may slip, or if you are going, it may wither. This side, it may disintegrate. Then the study won't be of the real sense. Now you are going with a small plunger, it is acceptable, and then you need some area where the sample should be like a sample, it should not be disintegrated. That's what this one. Another one, for apple, I am penetrating something, I am putting the solid platform and then apple. Okay, here like a small gel, like aloe vera gel, I am putting the same plunger, I am using it here. Suppose anything happens, means here also plunger can be used, but then you have to very cautious in setting the trigger points and the depth you are going in, and where to stop. And suppose you are giving something, what happen, this will penetrate, it will, you may not be knowing that, but the probe will reach to this point, and then the probe will get damaged. So here another one, there is a platform where there is a hole will be there, platform with a center hole, and then center hole you can put your aloe vera gel or soft material, then you make it a plunger. Anything happens, that will go inside, that is allowable, and you can go for it. So here, the plunger size, the gap, or it should not be, otherwise what will happen, the shear force also will come in. This shear force, it won't be of, suppose aloe vera gel is so soft, this shear, it will be material that is hard material to probe, that will be very peak value will be there, and if you take that value, you will be of wrong interpretation. So here lot of gap is there. If it is lot of gap is there, means this material itself, when I am touching, that will be not having the real sense of the probe pressure you are giving in, but that will have a deformation of it won't. So this is not good. Another one, the backward extrusion. See, first one, the sample, this arrangement I am putting in, and up to some time, this is become agglomerated, and then once it's happening again, it is bounce back. That is what the backward extrusion. Here what happens, all this area, that is very important. Suppose when you are repeating the experiment, the sample, that annulus space, that is very important. Another one, so I was showing the idli that sample. Suppose your sample has rough surface. I am putting the probe. The trigger point starts with the first obstacle when it meets the trigger point, trigger value. Suppose if it starts with the rough value, suppose if we are saying 5 mm, suppose it reach this rough value is 2 mm, and only 3 mm will go inside, and you won't get the value, the true nature of 5 mm what you are looking for, and then it will be a wrong value. Suppose you have a very weak material, and the triggering point, it is very cautious. What I mean, for an example, I can say, like, what when we go with high precision electronic balances, what we do is we switch off the fan even, or otherwise, the fan, that wind that will create problems for your probe, that transducers. If anything happens, if I'm measuring, that will be so like that. Here also, as I said, no, in a second, 500 data is coming, that much precious. It needs the trigger point. It should be so cautious. If it is like aloe gel like materials, delicate materials, then you should be very cautious of that. Okay, I'm giving you some glances, thinking beyond the whatever the usual the manual or the kind of the literature give. Just we can have how best we can whatever we studied in other area to this texture analyzer. More. Okay, so many models are there. I'm not going here. I think you would have seen that viscoelastic, viscoplastic, dashboard, the spring. I'm going with this, Kelvin model. This is generalized Kelvin model, and then the energy, all things will be there. The graph. When you read the graph, so okay, I'll show some of the things. Stress relaxation, creep test. Here I am coming. Stress relaxation. Whatever. Suppose your bread is there, or bun is there, or a cake is there. I am putting a load and then keeping for some time, and then I'm reading the data. So under load, some behavior. When I'm keeping the load, some behavior. After that, some other behavior will be there. So you can get a lot of data, apparent modulus, so on and so forth. You can see this. Again, with the how the material, with the elastic material, you have different one, viscoelastic and viscous. Then another one is stress relaxation. The same thing how we can do here. See this graph. That also very possible. The first one, for understanding I put it, and for model understanding I am putting here this one. Here the real in the text analyzer how we can do. Another one, creep test. Okay, here also the dashboard is there, but it is very parallel. So the behavior of the material will be very different. Okay, you can study here also. I doesn't have the time to explain this graph, but then you can do with the text analyzer. When I was studying for the pasta production, okay, so I was putting the millet into the wheat flour, refined wheat flour, and then we were making the things. During doing so, we were making our CAD design for finite element for making a machine, extruder machine. So both hardware and software we are working on it, and then we thought of using the technology. Can we study the incorporation of the millet flour with the refined flour, how best it is going? So it is similar to your 3-point bending. But then what we did is we put a lot of elements like 100, 200, like this 1,100 elements we put in, triangular elements, and then nodes, and then we studied. You can see the cracks, the red points, we got a cracks. So this is a very interesting to read, and then it can be published in any places wherever you want. And then it is like a combination of some of the softwares, and then having the data, then understanding those things. This is another one. Generally, we study for any food grains, any fruits or anything, geometry, and then this another values, arithmetic, geometric mean, so many things are there. But what we did is taking those data, mechanical stress and strain using this textualizer, and then the same thing we simulated in the finite element model, and then we compared with those things. So anything moisture or storage or with the processing, how best it is well with the finite element model. And in the ASTM, they have different values, how best you can have a similarity in values. Suppose 10% is allowable. If it is so, your model is accepted by ASTM, and then that can go as a standard for the ASTM. So your model out of the finite element and whatever you're getting, and then for a typical products, you can upload for IS that standards, ASTM standards. So the research can be taken to other levels. This is one of the modulus of elasticity for the pearl millet. Okay, so we were doing the dehulling process, and then we were doing. Now, so far I was explaining about the textural analyzer. The arms moves up and down. Only it gives force distance time. Now, the same textual analyzer, the companies are coming in with the same movement up and down, and then you have a camera here, you have a mic here. Suppose for your example, suppose kurkure is there. You are penetrating, you are crushing, it is coming, it is in a kurkure, like no, it is crispy, and the sound will be the acoustic property. Graph will have a lot of ups and downs, okay? And then the camera will be there to see the sample, how physically it is disintegrating. So when you put all this together, you will get other understanding that also coming in. I'll give a 5 minutes video so that you will, for different sample, more than food, can we apply this thing to any other commodity? See, this is the tension. This is a strip I am using. See, this is this is firmness I am testing for a bread. See, I'm cutting spaghetti like vermicelli. This is perplex arms. So this is a jelly, very jelly adhesive type. See this? Yes. Another one, how to strip off something, 90-degree angle. If I press, how much aerosol will come? See? Ball, muffins, balloon, compressing, bursting. Blade. Here it's a cutting, but the platform is it's an open platform, so that the probe will go inside up to that point. It's a cut, is a weak cut. See, that it's a weak. You can see here. It is a extruded product. It's a bread. So how we put it like a fingers, how we press like that, then you can design your own probes. Camera, how it is there. See, anything linear movement. Jelly type. It's a tumbler, plastic. It is forward extrusion. Up to this point, nothing is happening. After that, it is happening. So the graph will have a see this gel. See how it is pasting and they are taking out. This is Crammer test. See, whenever you are going for crispy products and not having the uniform dimensions, and then you should put it in a box, and then with the Crammer shear, you can have it. Multiple puncture. See, for this compression, pizza, how it is tiered. See, spaghetti, when I'm working for a packaging, then I should have the length, how much I can keep, so that now my packets will be good. Noodles. This is a cone penetrometer. Chocolate bar. To what length or what thickness I can make it for better packaging. These values will be very interesting to have other processing optimization. See, what is the pressure I have to give? So what is the dough quality? Suppose I want to make it as a sheet, and then now I am measuring the quality of the dough. The tenacity it withstand, that much the gluten, the bondage, and then what is the proofing time. So you can whatever we saw some of the other instruments, food instruments. So with those values also you can take to that range and you can correlate those values. Okay, this is some of my publications, and then so this is what I thought of sharing with you, and then the food texture and beyond, and with our investigation through understandings, and that will give a lot of meanings. And though we were looking the up and down and the even for powder technology also it is there. I have not shown. I was having in the previous one, but I forgot to put it in this. For powder, now the textural analysis is coming with the small rotation also. Now, with the AI and IoT, this instrument is going to have a greater change, and where the engineers have a greater role to go like a human touch. See, you can the right side, instead of going with the firmness, this and that, just it will handle a fruit, and then it when it touch like a bread, how you're testing, and then you are pressing, and the value will come. So that's the day it is coming in, and the research can go on that front also. So with this, whatever I learned through the some of the years, I tried to sum up with 1 hour. I took another 20 minutes also. Thank you one and all to be with me for 1 hour. Thank you one and all. Any 1 or 2 quick questions? Yeah, I'll be happy to answer, or otherwise put it in the chat box. We will answer you. So here the participants are in a wider range. So I thought of mostly I put it in the category of the PG, PhD scholars, and then a few young faculties were there. And I put my PPTs to cater those people, and I could not able to take other range of people. And I thought of accommodating the mechanical engineering, electrical electronics, and other people. So some of the few slides I took it that angle also.
Now open for discussion.
My name is Vinod Kumar. I'm a PhD scholar from TNAU. So it was an excellent presentation and simple, and it was good, sir. Thank you so much. So my question is, could it be used for any dynamic analysis? So far we are seeing static example, the temperature when it affecting the product or something. I know the texture before and after we have discussed. Anything that dynamically when changes with temperature, because many
Yeah.
process item with the
Yeah,
temperature.
yeah. Okay. So since it is like a instrument, they don't want to incorporate all the process what you are looking for. Suppose if you say a cooking with natural, like a normal cooking with the water and everything. Suppose someone will be interested with the blanching, or someone will be the microwave, or someone will be with the electrical assistant, and they don't want to incorporate those processes into the machine. What they did is, with this electronic gadgets of mechanical nature they want to give. Suppose you want to have a dynamic one, what you can do is you can have your range of that process and samples, no, you can put it 60 temperature, 70 temperature, yes, take it and put it in here. So like that, no, if you put and then you can correlate. So that is very possible. Otherwise, inbuilt and they don't want to give purposefully.
Any more question?
Sir, myself, Dr. Vishwanath. We are looking for purchase of a new texture analyzer. So what are the basic probes we need to purchase for a regular research in the food technology?
No, it goes with their budget, and then when you're purchasing itself, they will give some basic one, maybe 8 to 10 items they will be giving, and
Okay.
whatever the puncher or the small P75, P35, then P5, and needle type, and then the platform, then solid one and the whole. These things, 7-8 items they will give. If the budget, if you have, and then you can go for whatever things you can. Goes with the management.
So myself, Ruchika Zalpuri. I am PhD student from Punjab Agriculture University. So my question was, as I was talking about texture of powders, how can we test that?
Okay. Not so that's what in this slide, in this PPT, that slide missed. So that is another package. What they did is the same gadget with that attachment. That attachment, what will do? The probe is coming, the probe comes and then it will be rotating, and then that will be the two blades will be there. So it is coming down in the pack of your powder or flour, and then penetrates, and then small rotation. So during that time, the torsion, whatever I told, in the few maybe 10th or 11th slide, that will be effect will be there, and you can measure the powder values. And then you can derive to the more cycle, this, that, and then you can take to further levels. So what I mean to say is, more than the linear movement up and down, there is a torsion that also possible. That is a different attachment that is there in the texture analyzer.
Okay, sir. Thank you so much. Wonderful presentation, sir.
Dr. Bala, I have one query. Have you tested some experience of the animal feed, like poultry feed?
It is very possible for any muscle food, the fisheries, anything. And as he was asking for the poultry feed, it is very possible. See, poultry feed is again the composite of the agriculture and the muscle food waste and all. So whatever you want to make it, the extrusion, yes, that also the compact pellets, yes, I can go for mechanical strength. Whatever the volumetric, yeah, I can go for it. The length of it, I can optimize. So like that, I can study, sir. And I had I was having, when I was in Ludhiana, there was a collaboration between us and the another laboratory. There they study the drug delivery, pharmaceutical drug delivery with the mice, the rats. And that rat samples means that the bones will be coming. They were expecting that drug will give a strength to the bones will be coming very regularly. It was coming for us 6 months, and we were studying, and those pharmaceutical and then clinical side MBBS, those people, they were studying how the drug delivery goes into the mice, and that can be extended to the human studies also. That way, anything could be possible, and how you are making tie-up with the people.
It's my privilege to propose a vote of thanks for this webinar. So I first of all thank our Honorable Director, Dr. C.R. Mehta sir, ICAR Bhopal, for motivating and supporting and giving time to time direction for this webinar. Thank you very much, sir. I thank our Honorable today Chairman, the Project Coordinator, ICRI, Replacement of Animal Energy, Dr. M. Dean sir, for specifying the importance of and the need of this topic in the present aspect and also future needs. Very thank you, sir. Thank you very much. Thank our head of our regional center, Dr. S. Balasubramanian sir, who is also a speaker of this today webinar. Sir, webinar is very excellent, covering all part of the food texture analysis, and it is having a good introduction and also understanding and also useful for all application point of view for researchers. At last, it is an excellent coverage on the topic, sir. Thank you very much for excellent presentation. On behalf of our institute, CE Gopal, and our regional center, Coimbatore, I thank all valued participants present in this webinar.
Thank you, Unadol.